Kinematics. So this is the first part of the mechanics or the space and time section of the IB physics curriculum, and this applies to you both if you're doing HL and SL. Now, Vectors and Kinematics is very maths heavy. It's probably the most maths heavy part of the physics syllabus. So if you do high level maths, especially because of vectors, this will very much help you in this. However, I will be going over vectors anyways from scratch for what you need to know in the syllabus, especially for kinematics. And this applies to you both in HL and SL. So, vectors and kinematics. What is it exactly? Well, kinematics refers basically to the way that we look at movement anywhere in our universe. It can describe the movements of the tiny little air molecules that are hitting the heat shield of this spacecraft re-entering our atmosphere. It can describe the motion of this spacecraft, the speed at which it's going, the acceleration at which it's going, the direction. It can describe so many different things. It can describe the way that planets and, in this case, this is a supernova, and the way that supernovas expand, etc. And basically, kinematics and vectors describe the way that our universe works because it describes the way that it moves. In quantum physics, there's some slightly different rules, but pretty much everything else, even in atomic physics, we can apply the rules of kinematics to pretty much anything, especially anything in our day-to-day lives. Now, and in this course, I'm going to be going over everything you need to know about kinematics for your IB exams, and this is, like I said, in the SL and HL syllabus. So let's start off. Before I get into kinematics, I'm going to talk a bit about vectors. If you do IB, HL, AA maths, you'll know what they are already. But in physics, vectors are vital because basically everything has vectors, is a vector, really. Because just like this character from Despicable Me called Vector, he commits crimes with both direction and magnitude. And this is actually a really good explanation for what a vector is, despite I don't know how crimes can have direction and magnitude, I'm sure they can, because vectors refers really to anything that can be quantified, which means anything that you can associate numerical values to, that has a direction in its direction and its magnitude. So, and in physics, this is used all the time, really with so many different things, because in physics, in our world, we live in a 3D world. We live in a world that has both space and it can have magnitude. We can look at the magnitude of a force, the magnitude of movement, the magnitude, just the distance, and there's so many different things that you can associate vectors to. And in physics, it allows us to do some very complicated equations, and it allows us to really visualize our world in a 3D way and be able to do basically make predictions about our world. And especially in kinematics, it is super important that you understand it. Now, how is this physics? How does it apply to your course? Well, physics is mostly vectors, like I said, and I think it's easier if I apply an example to demonstrate vectors, especially in kinematics. So we have our character here, Vector, and this spaceship moving, right? And they're moving at around the same speed, but in different directions. Therefore, their movement can be represented by these vectors on our screen, where the length of these vectors refers to the speed at which they're moving. So we'll call this speed 1, and then we'll call the length of this vector speed 2. And what can we see? Well, the arrows are around the same length. So if we watch the animation again, we can see that, if it lets me, there you go. We can see that they're moving at around the exact same speed as one another. Therefore, the length of those arrows, those vector arrows, are the same. But they're pointing in different directions. Therefore, what we can say is whilst the magnitude of their vectors, their movement vectors are the same, so we can say that the speed of 2 is equal to the speed of 1. Because they're moving in different directions, their vectors are not equal to one another. So therefore we can say that, and the vector of speed, we call it velocity. So therefore, even though their speeds are the same, their velocities, velocity of 1 does not equal to velocity of 2. That's just one example, speed and velocity. We'll get more into what they mean, how we can use equations, and how this relates to the syllabus. And what we can see, well, yeah, that's basically vectors in total. That's basically vectors. It's that simple. Just arrows that represent direction by the direction of the arrow, and magnitude by the length of the arrow. Super easy. Let's move on. So, how does this actually apply to the physics course, the IB physics course? So, this is given to you in your data booklet. By the way, it's really, really important. I found my data booklet when I did the IB course for physics was my best friend. It was it was just knowing where everything was and being able to remember going back to the data booklet. Really, it's super important that you learn your data booklet inside out and you really, really know everything, where to find different equations in it and what different things mean. Anyhow, so this is given to you in your data booklet. And how does this help you with vectors? Well, I'm going to refer to an example to describe this, which is this spaceship moving. Now, the length of the arrow, remember, we called it the magnitude. And in this case, we refer, in this diagram, they refer to the magnitude of this vector right here, this purple arrow, as A. So we can say that A is the magnitude, or the length of the arrow. A vector, I should write, sorry. In this case, this is a velocity vector. So A would be the speed in this case, because it's a velocity vector of the spaceship moving. Now, what's really important is a vector in a two-dimensional space, which is what you really need to know for IB physics and IB maths. You need to know 3D vectors as well, but here I'm just going to look at 2D ones. And what's really important is that there's two components. There's the vertical component of a vector and the horizontal component of the vector. What do these mean? Well, let's go back to our little spaceship flying. What we can see is that because it's flying at a certain angle to the horizontal, so by this angle theta right here, we can see that it both has a speed going upwards. If we just projected its speed going upwards, it has a speed going upwards and it has a speed going horizontally. If the spaceship was just moving like this, it would just have a horizontal speed and no vertical speed. And the spaceship was moving like this, it would just have a vertical speed and no horizontal speed. But because it's moving diagonally, you can see that it both has a horizontal and vertical speed. But how do we calculate that? Well, they give us these equations right here, and I'm going to go over their derivations because it's really important to know, and it's super, super simple. Because it is really just right-angle trigonometry. Because look, if we have our vector arrow like this, and like I said, the magnitude, the length of this arrow is A, and then we have its horizontal component, which looks, it's an arrow like that, and then a vertical component like that. and let's call its horizontal component A sub h, and then its vertical component A v, like that. And we also see that there's an angle to horizontal. And for those who take maths or know any very simple maths, what we can see here is that it's actually a right angle triangle. And therefore we can just use very, very easy right angle triangle rules to find the horizontal and vertical component. Because we already know, if we know the length of the vector, then we can just say, remember, sine theta is equal to the opposite over the hypotenuse. And in this case, the opposite is AV, because the angle is here, and the hypotenuse is A. It's the length of the vector. Therefore, what we can say is sine theta is equal to the opposite AV over the hypotenuse A. And when we rearrange that, we can find that AV is equal to A sine theta. And there you go. That's the first equation. And the second one is really very much the same, except for we want to find the horizontal component. And remember trigonometry again, this would be the adjacent side to this angle. So what we can say is that therefore cosine theta is equal to, remember, adjacent over hypotenuse, so therefore we can just do AH over A. And then just again rearranging, we can find AH is equal to A cos theta. Super simple. And that's it. Now, the last thing that we need to know is what if we're given the horizontal and vertical component and we just want to find the length of the vector. We just want to find, in this case, if we have the vertical speed and the horizontal speed, what happens if we just want to find the total speed. Now this is the magnitude of the vector, and in this case it's just A, because they've written it out just as A. And remember, this time instead of using trig rules, we just use Pythagoras theorem, because remember, A squared plus B squared is equal to C squared. The adjacent squared times the hypotenuse squared is equal to the hypotenuse squared. Did I say that right? I don't know, but we'll see. So, therefore, if we know that AH squared plus AV squared is equal to A squared, therefore, we can just say A is equal to the square root of AH squared plus AV squared. And that's super simple. Just basic trigonometry. Right, let's move on to an exam question on vectors. Now we have a ball that's projected with an initial speed of 2 meters per second. So you can see, that the arrow like in this way, 2 meters per second. So we can say A is equal to 2 meters per second. And we say, and that it is at an angle of 35 to the horizontal. So this angle right here, we can say that theta is equal to 35 degrees. Which expression gives the vertical component of the velocity vector? Well, if we're trying to find the vertical component, we're trying to find this right here. Right? And we're given A and we're given theta, so therefore we just apply the formula from the previous slide, and remember that AV is equal to A sine theta. And now we just substitute our values in. It's equal to 2 times by sine 35. And then the unit for velocity is meters per second, so we just write meters per second. And is this one of our answers? Yes, it is. 2 sine 35 meters per second. The answer is C. Very easy question. This is in a paper 1, but yeah, it's really not very hard. You can see vectors in physics. It's not too hard at all. It's just trigonometry, really. Now, let's move on to some more kinematics. So we have 3 terms, and all of them are actually vectors, so I should actually put a little vector symbol like that. A vector, by the way, is always has, if something is a vector, then we say that it has this little line on it, or some people put a line underneath it. Some people just make it bold, but it doesn't really matter. In this course, you don't really need to worry about that. Anyhow, so we have 3 different components with displacement, velocity, and acceleration. Now, if you've done calculus, you'll be able to tell just by looking at what they're measured in that that velocity is actually the derivative of displacement, and acceleration is the second derivative of displacement, or the derivative of velocity. And if you haven't done calculus yet, I really urge you to look up online, do a little bit of basic calculus just to know what this means. It isn't as hard as people make it sound to be. Calculus is actually relatively easier. The basics of it is relatively easier. But it's really important that we know what derivatives are, because in kinematics, it's so important. But I'll go over their definitions real quick. So displacement is just the vector of distance. So if we have a person here and they start off at this point, we'll call it 0, 0, and they travel here to this little flag. And let's say they go like that. Like that. That's the path they take. Now the distance they've gone is the length here. The length of this right there. That is the actual distance they've gone. But the displacement refers to actually how much they've moved from the start point. So if we'll call this is the distance, and the displacement is this. Displacement is a straight line that tells us how far they've actually gone. And like you can see, it's a vector because look, it's got both magnitude, it's got a length, and it's got a direction. It went from there to there. But distance is just the value of actually how far they've gone. So here, let me just remove all this because it's kind of in the way. So really quickly, there you go. Right, so we know what distance is, and distance and displacement are both measured in meters. That's really important. And then we have velocity. Now, velocity refers to the rate of change of displacement. So if this guy, well, I shouldn't have deleted the guy, but yeah, if we have this guy here and he goes here, the velocity refers to how long it takes for this guy to reach from there to there. It refers to the rate at which this guy can travel. So if he can go there very, very quickly in just less than a second, then that means he has a very high velocity. And if he can go there very slowly, it takes him a lot of time. If the amount of seconds it takes per interval, like here, is really high, that means he's going at a low velocity. Therefore, we can define velocity, given by this v, as the rate of change of displacement. So the change in displacement, called delta s, over the change in time. So the change in someone's displacement divided by the change in that person's time or that thing's time. Now, we have velocity, and then finally there's acceleration. Now, same concept as the difference between velocity and displacement, except for acceleration is the rate of change of velocity. Therefore, we can define acceleration is equal to delta v over delta t. Now, one thing that is super useful in these IB exams is most of the time acceleration is kept constant, which means that in the questions that you'll be answering, which means that the acceleration, this value, the value here, doesn't change. The rate of change of velocity is constant. I'll go over what that means more in a bit, but basically what that means is, whilst with this, you can't always just do distance over time because the velocity doesn't stay the same. What we can do with acceleration is, because delta is equal to delta v over delta t, we can define delta v, the change in velocity, as the final velocity minus the initial velocity, which is given by u. So I'm just going to put up here, initial velocity u. Initial velocity is given by u. So delta v is v minus u. It's the change in velocity. And delta t, we'll just call it t. Therefore, if we substitute that into that, we find that a is equal to v minus u over t. Now remember, this is only the case when acceleration is kept constant. But in most of our exam questions, they do state acceleration as constant, and we can see that it's constant. So yeah, that makes things much easier for us. The last quick thing is that speed, because remember displacement is a vector and velocity is a vector, we can describe speed as the magnitude of that vector, of the velocity vector, because speed is given not in a vector, it's just speed is just a singular number and it doesn't have a direction, versus velocity does have a direction. And the same thing with distance and displacement. I've talked a little bit about that already. Now, motion graphs. This is really, really important. Basically, motion graphs is what happens when we graph these different things. And doing maths, you should be able to tell. So a velocity time graph, that means what happens if you graph velocity with time on the x-axis, or displacement with time on the x-axis. Now, there's two scenarios in your IB exams that you'll have to look at. This is the less likely to appear, but the much easier scenario, and this is when velocity is kept constant. Now, when velocity is kept constant, what can we notice? Well, velocity is constant, so it is just a straight line like this. And one really important thing is, because remember we defined velocity as the derivative of displacement. That means that velocity, you can find velocity by the gradient of a displacement time graph. So let's call this here. Here we have, in this case, where velocity is constant, because after each second, so if this is t1, if we look t2, the displacement, which is the area under this graph, is going to increase linearly. But I'll go to that in a minute. What's really important is in this same scenario, we can see displacement is a straight line coming from the origin. It doesn't need to come from the origin, but it's a straight line. And we can find the velocity, because remember, velocity is equal to delta v over delta change in displacement over change in time. So therefore, if we have the displacement time graph, and we have here the displacement, the change in displacement, the change in time, therefore we can just say that the velocity is this divided by this, and that is the gradient of this graph. And it would work in the same way if we did just this. And we basically just find gradients on this graph. And because it's a straight line graph, we can tell the velocity is constant because the gradient doesn't change in this graph. So what can we do then? Well, because the gradient doesn't change, velocity is constant, we can then say that velocity is equal to the distance divided by the time. Displacement divided by time. So we can just say it's s over t. And working backwards instead, if we have a velocity time graph, how do we find the displacement? Well, because velocity is the derivative of displacement, what we can say, if you know calculus, you can say that displacement is the integral of velocity, which means you can find displacement by looking at the area under a graph like this of a velocity time graph. So at a certain time, t1, we can find the distance that something's traveled based on its velocity, and if its velocity is constant, we can just find the area near the graph. And look, this is just a rectangle, which means we can just do the time here multiplied by the velocity. So therefore, when velocity is constant, we can just say that s is equal to v multiplied by t. And look, that is basically same equation. These two are the same equations, just rearranged. So yeah, that's really simple. When velocity is constant, physics is very easy. Now, what happens when it isn't constant? And instead, acceleration is kept constant. And acceleration means that velocity is changing and that velocity isn't kept constant and that it's either increasing or decreasing. So if acceleration is constant, well, look here, we can, when velocity is constant, we just found the area under the graph to find displacement. And it's the same thing. We can just find velocity from an acceleration by looking at the area under this graph. And when acceleration is constant, we can just say, oh, look, it's a rectangle again. Therefore, we can just apply the same rule and find the velocity is equal to the acceleration multiplied by the time. Easy. And then we can do the same thing if we look at the velocity time graph here, and if we find the gradient of this straight line graph, which is constant, we can just say that acceleration is equal to, well, the change in velocity divided by the change in time. Therefore, we just do this divided by this. So therefore, we can just do v over t. Sorry, that's meant to be a v. And look, again, these two are just rearranged. It's the exact same thing as this, but instead with a velocity with displacement, we have acceleration with velocity. Now, what happens, if it's not letting me undo, oh well. What happens then to displacement? Remember how I said it's the area under the graph? Well, this holds true. Except for this isn't a square or a rectangle anymore, which means we can't multiply time by velocity to find the displacement. That would give us double the displacement to what's actually there. And this time, the displacement is given by the area under this graph. And because this is a triangle, we can just use the area of a triangle is half base times height. And look, the height is given by delta v, and the base is delta t. So therefore we can say S1 is equal to half times by the velocity multiplied by the time. So the displacement after a certain given period of time is equal to half times by the velocity times by that time. And if we just work backwards here, what we notice is, because remember that velocity is the gradient of displacement time graph. You find the velocity at any given point by finding the gradient at a given point. But what do we notice? Well, the gradient isn't constant. It's constantly changing. And in this case, look, we can see if we draw little tangent lines to show the gradient, look, the gradient is constantly increasing. And that makes sense because the velocity time graph is also increasing. So therefore, what we can say here is we can find the velocity at any given point by finding the gradient of this at any given point. So if we draw a little line there and draw a tangent line, we can find the velocity by doing the change in displacement times by the change in time at that given point, and then we can find the velocity at that given point. And there you go. That is motion graphs when acceleration is constant. And now let's move on to an exam question. Now, the graph shows the variation of velocity v with time t of a car. Assuming there were numerical values on the axes, so pretending that we have these different values, which of the following could be deduced from the graph? First one, displacement. Can we know displacement? Remember, this is a velocity time graph, and the velocity is changing linearly. Therefore, like I said, acceleration, that means the acceleration is constant. And therefore, what we can do, can we find the displacement? Well, remember, displacement is the area under this graph. And look, can we find this? Yeah, because we have the change in velocity. We can just have the change in velocity and the change in time. Therefore, we can find the displacement by doing half times by the change in velocity by the change of half velocity times time. So we can find the displacement. Can we find the acceleration? Remember again, acceleration is given by delta v divided by delta t, the change in velocity divided by change in time, not multiplied by change in time, but divided by. And because, remember, this is a linear graph, therefore the change in acceleration stays constant. So can we find the acceleration? Yes, we can. We can just do delta v divided by delta t, so we can. And finally, change in velocity, that's just delta v, and we can just find it like this. So yes, we can. Therefore, the correct answer is 1, 2, and 3. We can find all three. Oh, sorry. Right then. Let's move on to the fundamental equations of motion. Now, these are the equations that are all given to you in your data booklet that allow you to make certain calculations. Very, very important. This is when acceleration is constant. These equations all apply only when acceleration is constant. Now, what's really easy is that, yeah, like I said, they give it to you in your data booklet, but what they don't give you is the different definitions for the different terms in this. So they don't give you what S is, they don't give you what U is, they don't give you what V is, and they don't give you what T is. So it's really important to remember these different units. So for S is displacement, U is initial velocity, V is velocity, A is acceleration, and T is time. And this is known as the SUVAT, and these are known as the SUVAT equations, and you can remember it that way. I'm going to go over the derivations of these two equations right here. Not that you really need to know them, but if you know how to derive them and how you come up with them, it makes life very, very easy for you in the exams. These two are quite complicated, so I'm going to let those. I'll just let you look at those, and what's important with these two is the fact that you can just rearrange them. But these two are the ones that are these two are the ones that are the most important that you need to know. By the way, this one requires a little bit of calculus for its derivation. So if you haven't done calculus, then feel free to just skip this derivation. So first one, v is equal to u plus at. The way we do this, I'm gonna color code this. So this one is in red, this one I'll do it in blue. So we remember acceleration is equal to delta v over delta t. But when it's constant, remember on what I previously said, that means that it can be given by v minus u over t. So the final velocity minus the initial velocity divided by the time. And therefore, just simply rearranging, we can just put at is equal to v minus u, and therefore v is equal to u plus at. And there you go. First equation, just a little bit of very basic algebra. Second one is also really simple. It's just calculus. We use this equation and do calculus with it, because we know, so what we do is that we know that the integral of velocity by time is equal to displacement. Therefore, we can just say we just substitute this equation here into v, into this one. Therefore, we can just say that s is equal to the integral of u plus at. And when we use the power rule, we find that that is equal to ut plus half at squared plus some constant c. Now, what's really important is that because the constant c in this case would refer to an initial displacement, a displacement that's happened when time is 0. But because we're just trying to find the change in displacement, we're not trying to find some total displacement, we can make our lives a lot easier by just saying c is equal to 0. Therefore, we can say that displacement is equal to ut plus half at squared. And there you go. We have our second equation right here. And that's it. These are your fundamental equations of motion. And what's really important is to get used to being able to rearrange those in different ways, being able to look at a question, figure out which equation to use based off of what information is given in the question. But there you go. Now, moving on, let's do an exam question. Now, an object moves in a straight line on a level road. The variation of the object's distance, d, with time, t. Oh, whoops, first question, whoops, define distance. Well, remember what I said? Distance, if we have someone moving like this, and this is where they're moving, and this is their path to get there, their displacement is the actual straightforward displacement that they went, and the distance is the actual distance that they traveled along this line. So therefore, we can define distance as length of the path followed. So we'll just put length of path followed. There you go. Now let's do B. BI. BI. Describe the motion of the object between time 0.5, so right here, and the time 1.0. Well, what can be seen about this? What we can see here is that describe the motion, that means we have to describe the way it moves. So therefore, we want to look at the velocity. So what happens here? So let's draw our tangent lines here, and then the tangent line there. What's noticeable about between these 2 points is that the tangent line the gradient of this tangent line actually decreases. It goes from like this to like this, which means that this gradient is decreased. And remember, because the gradient of distance time graph gives us the speed, therefore we can then say that between these 2 points the speed decreases. Or the object slows down. There you go. Let's do II. Calculate the instantaneous speed of the object at t is equal to 0.5 seconds. So we're trying to find the instantaneous speed of the object at right here. So you can just take this away and then put a little cross there. What can we see about this? Well, if we're trying to find the speed, then remember what I said is that we find the gradient. And we have to find the gradient at that specific point. So therefore, let's draw a tangent line at that exact point, like this. And then we can just make it a right angle triangle like this. Now, therefore, we have the change in displacement is equal to, here we can have 25, 26, 27, so that's about 28. So is 28 meters, subtract, and that's at 10 meters. 10 meters, which is equal to 18 meters. What's the change in time? Well, it's 1 minus 0, which is just 1 second. And therefore, we know that the speed or velocity is given by change distance, the speed is given by the change in distance divided by the change in time, which is 18 divided by 1, which is 18 meters per second. And there you go. Super easy. And that is the correct answer. Let's move on. On the axes below, sketch a possible graph of the variation of velocity v with the object time t. There is no need to add values on the axes. So what can we see from here? We can see that, again, looking at if we're trying to draw a velocity time graph based off of this distance times graph. And what we can see is, look, the gradient is constantly decreasing on this graph. So look, is constantly decreasing on this graph. Therefore, the velocity must also be decreasing. So we can say that, and remember, they're not normally going to ask you a question where the acceleration is not constant, so therefore we can just simply draw that the velocity is decreasing until a point here where it is just flat. The gradient is just flat, which means the velocity is 0. So we can just draw a straight line going downwards, which just shows the velocity decreasing. And that's 2 marks. 2 entire marks just for drawing that line going downwards. Right, now, there's the hardest part of kinematics in this course is projectile motion. And projectile motion kind of uses a combination of everything that's been covered involving vectors and kinematics in just an example. I'm going to fire this arrow real quick, and this blue arrow here, this bow and arrow, this blue arrow here represents the vertical velocity of this arrow, and the red arrow represents the horizontal velocity of the arrow. And when we fire it, what happens? What's noticeable, first of all, is that this red arrow does not change. It stays completely the same, actually, and it doesn't change throughout the entire time. Actually, at this point, they should both be 0 because they've just landed. But during the entire flight, this red one doesn't change at all. So the horizontal velocity of the arrow stays constant. But the vertical velocity, what we can see, is that it starts off like this, but as it goes up, it constantly decreases. Until here, it continues decreasing, and it's negative. What does that tell us? Well, it tells us that whilst the arrow is moving upwards until it reaches its maximum point, it's actually accelerating downwards, which means that there's an acceleration of the arrow pulling it downwards. And that acceleration is the acceleration due to gravity. It's gravity, because gravity is a constant acceleration that is present in the whole world on objects. But gravity only acts downwards. It doesn't act horizontally. It means gravity, acceleration due to gravity, there's no acceleration sideways due to gravity, only downwards. Which explains, and if this is, by the way, in the case of ignoring air resistance, which in most projectile motion questions in the IB, you will ignore air resistance. And for something like an arrow, you can really just pretend air resistance isn't there. But what we can see is that because there's no other acceleration in this direction, this arrow stays constant. But because there's a constant acceleration due to gravity downwards, this arrow right here starts off upwards and it's continuously decreasing throughout the entire motion of this arrow. Therefore, what are some quick good notes about this? Projectile motion, horizontal velocity is constant. Unless there's air resistance, it's constant. The vertical velocity decreases as the arrow approaches its maximum height. The vertical velocity becomes negative and increases in the negative direction again once it's reached its maximum height. So once it's here, its vertical velocity is actually 0, and it's only moving sideways. And you can see that because the tangent is just straight forwards. Vertical velocity becomes negative and increases again after it reaches its max height, and therefore there is a constant downwards acceleration, and that is the acceleration due to gravity g. And g is in your data booklet, and it is equal to 9.81 meters per second squared. Very important to know. Now, really quickly, how can we find the different, how then, if we want to find a certain period of time, both the horizontal displacement and the vertical displacement. So let's say here we want to find the S of H and S of V. We want to find its exact coordinate position by finding its horizontal and vertical displacements. Well, in the horizontal axes, we can see that this red arrow shows that there's a constant velocity. Therefore, because velocity is constant, remember our displacement time, our velocity time graphs, and velocity is constant, we can just say that S of H is equal to just the velocity, the initial velocity, which is the same as the final horizontal velocity. So SU of H times by the time. That's it. Now, in the vertical component, it's a little bit more complicated because this time the velocity is not constant. The vertical velocity is constantly is got a constant acceleration of g downwards. So really quick, first of all, let's try to use the equations to find the horizontal and vertical components of this arrow moving. Of the initial velocity of this arrow. So we have our horizontal component. So if we have the total initial speed of the arrow, we can then say, okay, and the angle, that the arrow is launched at, we can then say, okay, the horizontal component, the vertical component, is given by u sine theta, and the vertical one is given by u. The horizontal one is equal to u cos theta. Very easy, and that's fine. So now we have the initial vertical component of the initial velocity. What we can do is apply it to our formulas, one of our formulas, and that formula is going to be S is equal to ut plus half at squared. So one thing that's really important is in this case it's not a. Our value for the acceleration is just g. It's a constant acceleration. But g, acceleration due to gravity, like I said previously, is something that always acts downwards. So therefore, we represent it as negative. So therefore, what we can put is S of v is equal to u of v, the initial vertical component of the initial velocity, t minus half gt squared. And there you go. That is our two equations that describe both the horizontal displacement and the vertical displacement at any given point in time of this arrow's motion. Now, let's apply this to some problems. So our first one. A table tennis ball is thrown horizontally from the top of the building. The variation of the ball's horizontal displacement s with time t is shown in the graph below. State which quantity is given by the gradient of the tangent to the graph at any given time in the motion. Well, it's thrown horizontally from the top of a building, and the variation of the ball's horizontal displacement with time is shown in the graph. That's really important. They're trying to catch you out, but remember what the gradient of a tangent of a displacement time graph is? That is the velocity. So if we find the gradient right here of this graph like this, or the gradient right here, we get the velocity. And because this is just the horizontal displacement, therefore we get by finding the gradient at any given time at a specific point during motion, we get the horizontal velocity. So the first answer, B, I, horizontal velocity. There you go. Now, 2. On the graph below, sketch the expected variation of horizontal displacement with time when air resistance is ignored. The original curve is in a dashed line. Now, we can tell that air resistance in this dotted graph isn't ignored because look, even though it's thrown horizontally, its displacement isn't linear. It's curved, which means that the velocity must constantly be decreasing because look, the tangent decreases. The gradient, of the tangents constantly decrease. So therefore, air resistance is causing the ball its ball's horizontal velocity to constantly decrease. But if air resistance was ignored, that means that there would be no force acting on this tennis ball. So therefore, we know that it would be a straight line because the velocity would be constant. The horizontal velocity would be constant. So therefore, what we do, make sure we draw a straight line like this that has the same initial velocity, because remember when the ball was originally thrown, the air resistance hadn't had much time to act on it, so therefore it hasn't decelerated much, so the initial gradient is the same, but instead of curving downwards, because there's no air resistance, it would just go straight upwards. Now, finally, this is a 4-marker, and you'll see 4 marks, it might look intimidating, but really it's just a little bit long, and it's not actually that hard. Because what's really important, first of all, find what they're giving you. So, a stone ball A stone is then launched with a horizontal speed of 20 meters per second from a height of 12 meters above the ground. Determine the magnitude of the displacement, so the magnitude of the displacement of the stone when it hits the ground if air resistance is considered to be negligible. Now, what does it mean, the magnitude of displacement? Well, the ball, we can see here that the ball travels along this specific path like this. And if we found the length of this path, that would be its distance that it travels. But remember that displacement is a vector, and it refers to, this vector right there, here. It's a terrible drawing. And if we're trying to find the magnitude of the displacement, we're basically just trying to find the length of this vector right here. Now, what we can do is let's just draw this out just using trig instead. So we have this. This is what we're trying to find. We know that the initial height is 12 meters, and we don't know what this length is. So we know that this is 12 meters, and we don't know what this is, and we don't know what this is. But what do we do know? Well, it's launched at initial horizontal speed of 20 meters per second. So, therefore, what we can do, we can say that U of H is equal to 20 meters per second. And look, if it's launched with just a horizontal speed and not a vertical one, we know that U of V is equal to 0 meters per second. Sorry, I forgot my units. And that its initial displacement is 12 meters. So that means that for it to travel this way, that means it must travel a vertical displacement of negative 12 meters. So actually, this should be a little arrow like this, and that should be negative 12 meters. So we know that S of V is equal to negative 12 meters. Now, this tells us a little bit, because what we can do with this, what we can tell now is then we can apply this to our formula, which is UT, S is equal to UT plus half AT squared, because we're given that. So therefore we can say negative 12. So we know that S of V is equal to UV times by T minus half GT squared. Remember? And now let's just substitute values. U of V is 0 meters per second, so therefore 0 times by time is just going to be 0. So therefore, we can say that negative 12 is equal to negative half GT squared. Ooh, that is a terrible squared. There you go. And now with two negatives, we can just cancel things out and then rearrange. So therefore, we can just put 24 is equal to GT squared. And therefore, T squared is equal to 24 divided by G. And remember, G is 9.81. So if it lets me, there you go, 24 divided by 9.81. I'm going to move on to the next page because this is getting a little bit clunky. So what we had was T squared is equal to 24 divided by 9.81. And now just square root both sides of the equations. Therefore, T is equal to square root of 24 divided by 9.81. Great. Now we have time. We have the amount of time that it takes. Because of this, we have the amount of time that it takes for the ball to go downwards. Therefore, we have the amount of time it takes for the ball to reach this position here. With that, we can now find S of H. Because S of H, remember, if its air resistance is ignored, therefore the horizontal velocity stays constant, and they give us the horizontal speed is 20 meters per second. So therefore, what we can just find is we know that S of H is equal to u of h multiplied by the time. And we're given u of h. U of h is 20 meters per second. And we're given, we now know t. So therefore, is equal to 20 multiplied by the square root of 24 over 9.81. Now, if I just go on my calculator real quick, if I can find it, there it is, and put that into my calculator real quick. By the way, for your exams, get used to using your graphical calculator or whatever calculator you're going to use in your actual exam, because being able to use your calculator really quickly is super useful, because when you're doing an exam, time is always of the essence. So 24 divided by 9.81 and enter. That is approximately 31.2825, and then we round to two significant figures, because look, in our question it gives us everything with two significant figures like this. Therefore we can just say that that's equal to approximately 31 meters. So now we know that the vertical component, which was negative 12 meters, and we know the horizontal component now, which is 31 meters. And we're trying to find this, which is, therefore, what we can just do, remember the magnitude of a vector formula? We just apply the magnitude of the vectors, therefore, of displacement is equal to the square root of negative 12 squared plus 31 squared. And again, quickly using your calculator, what's that equal to? And my calculator just died. That's very useful. I think, let me just go back to the previous slide. I think I wrote down my answer somewhere. No, I didn't. 2 seconds. I'll just need to use my calculator on here. Let me just remember what I was putting in. It's the square root of negative 12 squared plus 31 squared. Square root of negative 12 squared. Negative 12 squared plus 31 squared. And that gives us 33.242. Oh no, it deleted everything. Oh no, it didn't. Oh, it kind of did. That gives us 32.242, which is approximately equal to, remember two significant figures, that's 2 meters. And that's our answer. Let me just make sure that I remembered that correctly. No, that was 33 meters. Sorry, I didn't write it into a calculator correctly. 33.2 meters, which is approximately 33 meters. And there we go. Here's our final answer. And that concludes everything about projectile motion and everything about kinematics and vectors that you need to know for this course. And you can see, whilst it may be a little bit maths heavy, it really isn't too hard if you know what you're doing. Thank you very much for watching,